this lecture is going to introduce the second half of Chapter 10 and talk a little bit about the first of the methods in that second half. All right, so the first half of Chapter 10 dealt with this question. I've got a population. I want to know some parameters, so I draw a sample and compute a statistic. And then I want to know whether that parameter is equal to some constant. So, we've done the delivery time problem where we draw a sample of packages and we want to estimate the mean delivery time. We want to find out if that mean delivery time was different than some constant. Okay, so that's what the whole first part of the chapter was about, was whether a parameter equals a constant. We also did problems involving percents. So is the percentage of people equal to some constant? The last half of Chapter 10 is going to deal with an extension of this idea. So instead of having a parameter equaling a constant, what we're going to be dealing with is whether two parameters are equal to each other. So does the purchase intent of males equal the purchase intent of females? So we're not comparing a parameter against a constant, we're comparing two parameters against each other. So to kind of get us into the second half, I thought I would talk a little bit about how the data for such problems arise typically. I mean, there's more than one way for these data to arise, but this is the typical approach. So there are two broad approaches of generating such data, and depending on how the data came about, we're going to use either the paired sample test or the independent sample test, which is later on in the chapter. Okay, so let's start out with the paired sample test. So very often we do studies where the defining characteristic is we take two measurements on each subject. All right, so every subject or every sampling unit we gather, we take two measurements on that person. So this commonly occurs whenever you have a before-after study. So, the classic example would be something like blood pressure. So I recruit a bunch of people, I measure their blood pressure. Then I put them on some new, blood pressure medication. And then I take a measure of their blood pressure again. So the point is, every person gets their blood pressure measured twice. Once before the intervention, in this case, giving them some new drug, and after. So I measure their blood pressure, I put them on the drug, then I measure their blood pressure. Or I recruit a bunch of people, I measure their weight, I put them on a diet, and then I measure their weight again. Or I measure your attitude towards my brand, I show you some advertising, and I measure your attitude towards the brand again. All right, so these are, that's one way of generating data. Whenever you've got two measurements on the same units, then you're going to use something called the paired sample t-test, which is the first section we're going to talk about today. Okay. The other approach is this. This is where you have two different populations, and you take a measurement on the units from each of those populations. So this usually comes about whenever you have a classic A/B test. All right, so using medical jargon, you have a treatment group and a control group. So you have a bunch of sampling units, you divide them up into two groups. One group is the treatment group, one is the control group. That's what TG and CG stand for. The R's indicate that you randomly assign people to these two groups. The treatment group gets the new and improved treatment, the control group doesn't, and then you take a measurement. All right, so in the case of marketing, this happens all the time. So I've got a banner ad, and I've been using this banner ad for a while. Now I'm going to make a new banner ad. So I want to find out if the new banner ad is any better than the old banner ad. How do I test this? Well, what I'm going to do is take a random sample of visitors to my website or wherever I'm exposing these banners. Some people get the old banner ad, that's like the control group. Some people get the new banner ad, that's the treatment group. And then I see what happens. So I measure click-through rates, I measure buy rates. So I observe whether they click or whether they buy, and that's this measure. Okay, so the point here is you've got two independent samples. Those who get the old ad, those who get the new ad, and everybody gets measured once. So do those who see the new ad click? Do those who see the old ad click? That's it. Your homework is going to involve another really nice example of this from personalization. So people at a German bookseller, this German bookseller was testing personalization. Your homework is going to be to analyze whether a personalized contact point did better than a one-size-fits-all contact point. So the control group, a bunch of their customers got the one-size-fits-all. An independent group of their customers got a contact point that had some personalized recommendations in it. And then you have a bunch of measures of whether they bought a book based on that contact point and also how much they spent. So whenever you're in this situation, you got two independent samples with one measure each, you're going to use something called the independent sample t-test. Okay, we're going to start with the dependent sample situation, which is a little bit easier to understand than the independent sample situation. And I know the order in the book is a little bit different, but that's okay. We're going to start with the easier one. So dependent samples, again, whenever you have two measurements on the same sampling unit, you've got this paired sample. Often it arises because of pre and post measures. What do you do in this case? Well, the analysis is really very simple. All you have to do is compute the difference between the post and the pre measures, take the difference between the two measures on each unit, and then you do all your single sample stuff on the on the differences rather than on the measure, the raw measurements themselves. All right. So what I thought I would do now is a problem from Siegel with you. I've typed this into Word, so you don't have to have your book. It's problem 10.5. Now 10.5 is actually in the single sample section of problems in the book, but it's really a paired sample test. So let's go through this. Some of your advertisements seem to get no reaction, as though they're being ignored by the public. You've arranged for a study to measure the public's awareness of the brand both before and after viewing a TV commercial. So whenever you see before after, that's usually, but not always, an indication that you've got one of these paired sample t-tests going on. So you're going to measure their awareness of your brand before seeing some TV show that has the ad in question. Then you're going to do this, you're going to measure the same thing afterwards. So again, every person who's viewing this TV show has two measurements, one before, one after. So you wish to see whether the ad had a statistically significant effect as compared with zero. Now, zero is really important here. Zero means no change. Okay, so if I take your before measure and your after measure and I subtract them and it's zero, that means that the before measure was the same as the after measure and has zero effect. So zero means no effect. Your brand awareness measured on a 5-point scale was found to have increased by such and such. Okay, let's not look at our data yet. We're not going to do any data snooping. Let's start out by identifying the parameter. So I'll just type it in here rather than writing it. It's kind of faster to type. So before you look at your data, you ought to state the null and alternative. So we're going to first start out with the parameter. Let mu, or we could use let me just see, I think it's option M. Yeah, okay, cool. Let mu equal the true mean difference. And what do I mean by the difference? So post minus pre so the true mean difference in brand awareness. So if I could do this to every person in the population, where I could measure their post score and their pre-score with the ad shown in the middle, then I would know mu. Compute the mean of all those differences, so these differences, then I would know mu. All right, we shouldn't data snoop, so let's go state our null and alternative hypothesis. The null hypothesis is that mu is equal to 0. The alternative is that, so notice what, let's go back and read this problem really carefully. A statistically significant effect as compared to 0. So the effect is not specifying a direction. So effect just means something is different from that. So then mu, and then we can use that as not equals 0. All right, so there's our null and alternative. Let's go read on. So we now go gather some data. So we talked to 200 people, and we find that the average increase, we find the differences between the post and the pre is 0.22. And we find that the standard deviation of the increase, so we find all these increases, was 1.39. So we've done part A already. Part B is perform a two-sided test by finding the p-value. And so I'm going to go do this on the scratch pad. And what I strongly recommend you do is take some notes. So what we've been told is that, got to figure out how to write here. X bar from our sample is 0.22. We've got a sample size of 200. We've observed the sample standard deviation, and that was 1.39. Now before you do anything else, go find your standard error. You'll almost always need the standard error in these problems. So the standard error here is equal to 1.39 divided by root 200. Go take out your calculator, and this is equal to 0.09829. You take 4 accurate digits with you. Now, at this point, we're kind of back in the first part of chapter 10. So we're going to assume that H naught is true. H naught mu equal to 0 is true. Now let's go draw what this implies. So this is the sampling distribution of X bar. So the sampling distribution tells us what happens if we draw a sample. And under the null hypothesis, the mean of this distribution is going to be 0. And we know that the standard error is 0.098 something or other. All right. Now, we have gone off and collected 200 observations from this population and observed a statistic of 0.22. So if we want to test this hypothesis, it amounts to us evaluating the area in this tail. So let's go find the area in that tail. And here's how we do that. So what is the chance of being in that tail? Well, it's the chance of observing an X bar value being greater than 0.22. Now, we know from the central limit theorem that this is going to be approximately the same thing as us having a z value greater than 0.22 minus the mean. Well, what's the mean? We assumed it was 0. Dividing by the standard error, which is 0.09829. Now, if you take out your pocket calculator, this is equal to 2.24, I believe. Now if you go look this up in a normal table, this is equal to 0.0126. So what that's saying is that there's about a 1% chance that you're sitting in that tail. So the whole story would be this: if the true mean difference is 0, representing no effect of the ad, so if the ad has no effect in the public, the chance that you draw a sample of 200 people giving a test statistic that's 0.22 or bigger is only about 1%. So that's not very remote. This 1%, however, is not the p-value. So your p-value, recall we have a two-sided alternative, is as follows. So since we've got two tails, it's going to be 2 times 0.0126, and that's equal to 0.0252. Because we have two tails, we're going to add that symmetrical tail over there as well. Final p-value is that. Now, if you go back to the course packet and read this really carefully, it says you're supposed to find out whether there's a statistically significant effect as compared to 0. So remember, statistically significant means you've got a p-value less than 5%. So you're going to use the cutoff of 5%. So since this is less than 5%, we reject H naught. Now, I'll just go type in the conclusion over here. This is, so since 0.0252 is less than 5%, we reject H naught and conclude that awareness is greater after seeing the ad. So that's our conclusion. One more thing. We could also do this with the confidence interval approach. So confidence interval approach would say find the confidence interval. So the confidence interval is 0.22 plus or minus 1.96 or 2-ish times the standard error, 0.09829. You'll note that this confidence interval does not include 0. So 0 is not in the confidence interval, which tells us the same thing, reject H naught. So that's it for this problem. There is another video, so I encourage you to watch this video that will show you how to do this with raw data. It'll show you how to do it in SPSS, and so I encourage you to watch that video now.